So now, if I want to just formulate the general learning problem, which includes the problem of data generation that we are interested in this course on, the general task in a learning problem is that we try to understand what is the data distribution. Either we understand it explicitly or we approximate it, right? And you might tell me that, well, this is not immediately what I can remember from many machine learning courses, like we have done classification, right? We have done regression, we have done clustering, we have done, I don't know, PCA, right? We have done all of this stuff, and we never have looked at this as a kind of distribution learning, right? But the point is that essentially whatever you have done there was distribution learning from a computational point of view. And if you just change your classes into statistical classes, then you're going to see it again as a distribution learning. So how it comes, let's try to look at the problem that you had before first. So for instance, all of you know about the supervised learning. This is the classical problem everybody starts with. And that is the problem of, for instance, classification or regression. And in this problem, you always have a data set. The data set includes a bunch of data points, data samples, x's, and also a bunch of labels, right? A bunch of label y, right? So x's could be images, y could be cat, dog, frog, so on, right? And then what you do when you always think about it computationally, this is, as I told you at the very beginning of this, in the first session, this is the easiest way of thinking about it because it's always about, you know, numbers. So what you think that whatever the class, the label is, this is coming out of a function, right? And we don't know what that function is, so what we want to do, we want to essentially learn that function by putting some model, right? So we put a neural network, x goes in, and then we get the label. And then we fit it into the data set. This is the computational point of view we all are used to. But we can look at this problem from a statistical point of view. Same problem, we just put the solution or put the method we are doing in different words. This is the only difference. So from a statistical point of view, what we are doing, we are having access to a data set. And as I told you last time, data set is a random generation or collection of a few samples from the data distribution, right? So you have access to these samples coming from the data distribution. And the thing that you are doing in supervised learning is essentially to learn this distribution. You want to know how label is distributed given one particular sample. This is the whole thing that you are doing. And if you do know what is the data distribution, the joint distribution of the label and the sample, you can essentially compute this guy, right? How can I compute this one from the joint distribution? If I have p of x and y, how can I compute p of y given x? I divide p of x and y with p of x and y. If I write it down in this form, p of x, then what is the next term? Chain rule? P of, everybody, I know it's late, but y given x, right? Y given x, correct? So p of y given x is simply p of x and y divided by px, right? This is the definition. Actually, this is definition. Chain rule comes out of the definition, right? So you can always write it down in this form. And how I can get p of x? Can I get p of x if I know p of x and y? Can I do it? Yes, I can do it. We're going to talk about this because this is important, even though it's simple. We can just marginalize this guy, right? Add it up over y, and then you're going to end up with this one. We're going to talk about it. But the point that I want to say here is that you always assume that you have a p of y given x, and you put a model for that. This is what you have done in classification, regression, whatever you have done. And you try to just find out or somehow estimate the original conditional distribution by your model. So let's take a look at the main examples you can remember, because I'm not sure if everybody's going to buy my words. So you might tell me that whatever I have done, for example, for classification or regression, didn't seem to be such a thing, right? So, and I can show you that this is really the case. For instance, what about classification? When you want to do classification, what do you do? I mean, think about the model. Don't think about the process yet. Just the model. What does the model do? It's going to get the image as the input. It's a CNN, for instance. It does all the calculation. What you're going to get at the very output? Probability out of a softmax, right? And then you're going to take the guy who has the highest probability, right? So essentially, your whole model plus the softmax as the output is the model you consider for the conditional distribution in your data. Yeah? And then your samples are helping you to just tune that model, to just train that model, right? So essentially what you do in classification, you literally compute that conditional distribution. So you always compute the probability of every label for a given data, and then out of that you do your decision, right? And if you remember what people usually do in basic machine learning, you see that if you don't define that probability, that softmax, that sigmoid at the output, you essentially cannot train a model, right? The model is not going to work. I mean, it's going to fail, right? I mean, for very basic examples, it can work, but when you make it like a serious example, you have no other choice but putting those probabilities, right? It's always the case. And what you literally do, as I told you, you have one model. This is your neural network. This is taking the input. Input could be your image. And then you compute a bunch of logics out of it. And out of that, whatever you do, whatever the model is, at the very, very end, you're going to put one softmax, right? And this softmax is going to compute for you the probability of every single label given your data, right? Conditioned to that particular input, right? So what you can say from the very beginning towards the last output of the softmax, I have one model for the conditional distribution. And what I am doing, I'm essentially training this distribution on my data set, right? Now, what you typically do when you want to train this model, what do you minimize? Cross entropy, right? You compute cross entropy, you average it over your batch, and you minimize it, right? So in the previous chapter, I showed you cross entropy, when you minimize cross entropy, it's equivalent to do what? Maximize likelihood, right? So again, you were not doing, from this point of view, you were not doing anything specific. You were just maximizing the likelihood, right? So you put one model for the distribution, and then you get your data points inside the data set. You put it inside your model. You compute the likelihood. Then you play with your model to maximize the likelihood, right? This was what you did in classification, even though most of us, as I told you, are used to think about it from the computational point of view, because that is easier, right? Everybody's clear? Questions? Now, classification is quite simple. So moral of the story, classification models always compute this conditional distribution, the distribution of label given input. But what about the regression problem? Regression problem, I mean, it's a bit different, right? The label is not anymore a class, right? Label is a real valued scalar, for example, right? And then you want to predict the value, you usually compute MSE and you try to minimize MSE, right? And you might again tell me we don't remember of having any probability involved when we were doing regression, right? But again, I can show you that you have done this essentially. Whatever you have done in regression was nothing but training a conditional distribution on your data set. So how is it? Let's look at the problem again. So what you have in regression problem, you usually have a bunch of data. So every single X has a label. But that label is not anymore a class. This is a real valued number, right? For example. And then what you do, you always consider one model, which is taking X and give you one real valued label, right? And that is the output of your model. So this is Y hat. And you hope that this Y hat is as close as possible to your original label Y, which you have inside your data set. And to do that, you just minimize the empirical risk, right? So what kind of model this F is? Any suggestion? What can I put here? Simplest model you can think of? Linear regression, right? You're going to put a matrix or a weight vector, and then you multiply it to the input, then you get the output. This is the real valued output. This is what you take as your output, right? So you might tell me there is no probability involved here. There is no distribution involved here. So let me just recap what we do when we want to train this model. So we essentially just compute the risk. How can I compute the risk? The risk is going to be the difference between the output of the model and the true label that I have, right? And the output of the model is essentially the model that I postulated. This is, for example, the linear model in the linear regression. This is the output of the model, and then I just subtract it from the label. And if I think of MSE minimization, then I just compute this squared error, right? And typically we do empirical risk minimization, meaning that we just average it over a batch, right? We have a bunch of data samples, so we average it over that. And then we minimize this guy with respect to the model, right? With respect to W. Now, what you can see, if you just put everything in order, is that essentially what you're doing here in all of it, essentially what you're doing, you're assuming that your label, this Y value, is normally distributed with mean being computed with the model you have, like the linear regression model, and a fixed variance. And you might tell me, how does it come? Well, yes, this is true, but we can actually only look at the maximum likelihood, right? So you just think that, forget about what you did in classical regression problem. Assume that you want to just fit this model into your data, and then you want to do maximum likelihood. So what you're going to do if you want to do maximum likelihood with this model here? Gaussian. Put your samples, and then you try to find W such that the likelihood is maximized, right? Perfect. Exactly, exactly. So you're seeing it exactly. So this is what we do. So let's do it together now. So say I want to compute the likelihood. So I have the distribution. This is the distribution here, right? If I think of one single data point, what do? I put that data point inside this distribution. This is my likelihood, right? And this distribution is the Gaussian distribution, right? So I'm going to write down the expression for the Gaussian distribution. This is a constant. So here is e to power mean minus y. Y is the variable here. And divided by 2 times the variance, right? Everything is easy, right? Now, since I have a data set, the likelihood of the whole data set, how I can compute? Just multiply them, right? So I'm going to multiply all of them. So I have n different data points. I compute this likelihood for every single of them, and then I multiply them, right? So this is going to be likelihood, right? Now, product of lots of exponential, what's going to happen? I can keep the exponential, and then I can take that product as a summation inside the exponent, right? Everybody's clear? So this final term that you see, this is your likelihood. Clear? Right? Now I want to maximize this likelihood. I don't like to work with likelihood because it has exponential function in it. Instead of that, I'm going to do log likelihood, right? So I'm going to take a logarithm of this expression. It's going to be this one, right? Now, you look at this expression. Do you see your empirical risk here? Yes. That summation that you see is non-normalized version of your empirical risk, right? So that guy divided by the number of samples you have is your empirical risk, right? So I can essentially replace this guy with this expression here, right? So my log likelihood is essentially proportional to minus the empirical risk, right? Now I want to maximize the log likelihood. What should I do to the empirical risk? I minimize it, right? So essentially maximizing your log likelihood, and that model, that Gaussian model we considered, is equivalent to minimize the empirical risk on the original regression model F, right? So moral of the story, again, in the regression, you are just learning the conditional distribution. right? So whatever you have done before in regression and classification was nothing but just learning the conditional distribution. Everybody's clear? So now you buy my word that you used to always find the or train the conditional the data distribution, and the classical method that you use is always log likelihood, right? Maximum likelihood, right? You compute the likelihood given your data set, and you maximize it, right? So this is a kind of general recipe for any learning problem. You just consider your data distribution, either explicitly or implicitly, and then you try to maximize the likelihood for that model, right? And you hope that your data has so much redundancy in it that despite its very high dimension, at the end of the day, it can be explained with a few samples. Okay? So this is the whole idea. This is the whole thing that we do in machine learning. Even though there are lots of branches to it, at the end of the day, we're always doing that, right? So now, moral of the story in summary, if I want to summarize everything, when you do supervised learning, you always postulate one model for your conditional distribution, the distribution of the label given data, and then you use maximum likelihood on the data set you have to train that model. Okay? That's it. Now, one thing is that here we are always talking about a conditional distribution, the distribution of your label given your data, right? And in both cases, like classification and regression, as you can see, you assume directly one model for the distribution of label given data, right? So you assume, for instance, linear regression is describing that one. That Gaussian distribution is the distribution of your label given data, right? Or for example, the softmax is just modeling the distribution of the label again given your input, right? So you directly assume that you have a model for this guy. This is what we call a discriminative model. And when you use maximum likelihood to train a discriminative model, you're essentially doing discriminative learning. So why we call it discriminative? Because we'll look at X and we want to suppress any other choice. We want to see which choices, which labels are the right ones, right? So this is the classical one that you do, and you can define it always in this form. So any discriminative model is the model which is describing the conditional distribution of your label. So this distribution of your label for a given data sample. Everybody's clear what discriminative model is? Okay. So in supervised learning, as I told you, you used to do discriminative learning, but there had been also a few other examples in basic machine learning courses which are not supervised, right? So we call them unsupervised learning, right? And in unsupervised learning, what you do typically? What do you do in unsupervised learning? One example. Can you give me an example? Clustering. So in clustering, what are you doing? You see a bunch of samples, and then you want to somehow understand a kind of pattern inside these samples, right? So you would say, okay, these samples look like they are being clustered into two groups, and then maybe I can find a model which somehow describes each cluster, and then any new sample that comes, I'm going to give it to this model to find out which cluster it belongs to, right? And then it helps me to group the data samples, right? So here you don't have any label anymore, but essentially you're looking into a pattern inside your data. And indeed, what you were doing generative learning in that case. So you were doing a very primary version of what you are right now looking for. So the models that you trained there, they were theoretically able to just generate new samples for you. But the point was that the models are so simple that they're going to just give you meaningless samples. They're not a good approximator, but they are essentially theoretically capable of doing that. So let's break it down together. So let's consider one unlabeled problem. So you have an unlabeled data set. X's are a bunch of samples which have no label. And what you look for in the computational world, you always say that I am looking for one particular model, like FW, which is going to describe the pattern hidden inside this data by looking on the samples. And the best example you can always think of is clustering, right? So you're going to give a data set of a few samples, and then you want to train a clustering model. And this clustering model, when trained, it is able to get a new sample and give you one cluster, right? So any new sample that comes, it's going to put it into one of the groups. It doesn't say, I mean, there is no ground truth for that anymore, but here it's going to help you to just clusterize different inputs. And this is typically the thing that we use, for instance, when we want to do anomaly detection, right? So if you want to know whether one sample is a normal sample or not, right? So this is what we used to do, or how we used to describe it in the computational world. But again, if you want to think statistical here, what you can say that data set D is essentially a collection of samples drawn from one distribution Px. And what you are trying to postulate, model the data distribution by a parameterized model like Pw. And then you try to somehow tune that model, train that model in a way that is approximating the true distribution as close as possible. Yeah? Now, just to make sure that everybody agrees, let's just take a look at the clustering problem. So, anyone knows about a famous clustering algorithm? K-means clustering, right? K-means clustering. Good. So what do we do in K-means clustering? So if I want to cluster one new sample X, what do? Usually we have K different centroids, right? Now, we're going to look, sorry, anyone? Yes, we start with a bunch of random points and then we train it. Now say we have the centroids, right? So we have K different centroids, and if you have a new sample, how do you decide for the cluster? You're going to look at that sample and find the distance to each centroid. The centroid which is the closest, that guy is going to describe the cluster, right? So this is the idea. So essentially what you do, if you want to find out what is the cluster of X, you're going to find the distance between X and all the centroids, and then you're going to take the guy who is giving us the closest or the minimum distance, right? The closest centroid, right? Now, if you want to train this model, what are the parameters that you can train? Centroids? Yes, and which sample belongs to which cluster, right? So, and how you do it, you just start on your data set, you just say, okay, a bunch of, these guys belong to this one, these guys belong to this one, and so on. And then you compute the total distances, right? So each point inside the data set, its distance from the corresponding centroid. You add them up, and then you keep on optimizing or iterating between two optimizations till you converge to the minimum possible distances, some distances, right? So this is the idea that you train it, and this is going to give you the K-means clustering. But if you think a bit from a statistical point of view, what you're doing in K-means clustering is nothing but modeling your data distribution to be of this form. So essentially what you're thinking, you're assuming that every single sample that you see is coming from K possible Gaussian distributions. One of them, okay? So there are K different Gaussian distributions. Each of them has a mean which is exactly the centroids, and the variance is the same for everybody. And what you're doing, you're just trying to find out which guy is generating this particular sample, right? This is the model that you are considering for your data in K-means clustering. And the cluster of your sample is essentially the distribution or the index of the distribution which is generating that particular sample. Now, if I assume a distribution, how can I find out which distribution is giving my sample? Maximum likelihood again, right? Yes. What you're going to do, if you see a new sample, You would say, okay, I have k different candidates as distribution. I'm going to put this sample inside every single of them. The one which gives me the maximum likelihood, that guy is the right distribution, right? So let's do it together. Say that I have k different distribution, all of them being Gaussian. Mean is the centroid, variance is fixed. So now I want to do maximum likelihood estimation. So how can I do it? I would say, okay, cluster of my new sample is the index of the distribution, which is giving me the maximum likelihood, right? Now, I don't like likelihood. I just replace it with the log likelihood, right? Fine. Now, if I think of a Gaussian distribution and I compute the logarithm, what's going to happen? Only the exponent going to remain, right? So if you take the logarithm, it's going to be something like this. But none of those terms depend on the index. The only term that depends on the index is denominator of this fraction, right? Which is, again, the distance between your sample and the centroids, right? So if you want to maximize that likelihood, instead of doing it, you just minimize the distance, right? So this is equivalent to just minimizing the distance. And this is exactly the thing that you do in k-means clustering, right? So again, in k-means clustering, what you're doing, you're assuming a distribution for your data. You assume any sample is coming from one of those Gaussian distributions. And now, when you want to do clustering, you just find the distribution which gives you the maximum likelihood, right? Yes?
But then when we are writing algorithms, respective algorithms for different problems, why do we not follow this approach and rather stick to the distance approach where we are randomizing and then we're selecting a centroid and then iteratively until we're converging, the previous iterations are not changing the outcome for those clusters. But if this is clearly an optimization, you make it an optimization problem by doing the maximum likelihood. So why do we not use this? This is much more.
Yeah, this is actually for in many probabilistic machine learning textbooks. This is the way that they explain it. So if you take a look at Bishop's book, for example, he starts by saying directly that I want to solve this problem by maximum likelihood, and then he ends up with k-means clustering. And all of the extensions of k-means clustering, essentially you can explain it from this point of view. So you would say, for instance, if in this basic k-means clustering, I'm assuming that everybody has the same variance, all the distributions, right? But you can put the distribution also to be a learnable parameter, right? The variance to be a learnable parameter, right? And then you're going to get the more advanced version of k-means clustering. Or for instance, you have the other version which is called the soft k-means clustering, right? And there, again, you don't say that your sample is definitely coming from one distribution. It comes from a superposition of all the k distributions, right? So many textbooks start from that point of view. But as I told you, this is when you have a good understanding of the statistical viewpoint. For many people, computational viewpoint is the dominant one. And because of that, it's hard for them to understand why this is maximum likelihood.
When you're writing an algorithm, why can you not follow the structure?
The structure of what?
The structure of maximum likelihood.
Yeah, as I said, like if you look at all those textbooks, they develop all the algorithms by this approach. So for someone who is a statistical guy, anything that you do in machine learning is always maximum likelihood. So this is not a kind of new development. This is like most people who work in this domain are used to this idea, actually. But as I said, like when you want to teach it into people coming from computational background, like many people doing engineering, then it's a bit hard to think about it from a statistical viewpoint because they don't have a clear understanding of how you can describe data as a random thing, right? But once you have that understanding, all of it is just maximum likelihood.
One more question.
Yeah.
Might have a problem with k-means that if we select the wrong initial point, we might not converge.
Yes, but that is not related to this one. That is related to the fact that the optimization problem you're solving is an integer optimization. Integer programming, and because of that, you are not guaranteed to converge to the global optimum. So it has nothing to do with this one, actually. That is indeed because of the whole optimization algorithm issue. In both cases, it's the same thing.
And this is just like one of the steps where we
Yes, yes. The point is that I'm just here talking about clustering, but then you need to consider all the samples you have inside your data. So you compute the complete likelihood, like the product, and then you just do the optimization. And of course, you can always define the binary variable, because each sample that you have has two randomness in it. One is the Gaussian, and one is the index of the Gaussian, right? And then when you write it that form, then you're going to end up with the exact k-means clustering algorithm that you have for training, right? Yeah. Questions? Everybody's clear? So, moral of the story, in unsupervised learning also, what you're doing, you're again trying to learn data distribution. So you assume one data distribution for your model, for your data, and then you try to fit your data set into that model, and simply you always use maximum likelihood. Okay? But now, one thing interesting that is happening here in unsupervised learning is that you are not anymore learning the conditional distribution, right? There's no label here, right? You're essentially learning the distribution of the data itself. You're learning px, right? And as we talked last time, if you have px, you can generate new samples, right? You sample from it, then you get new samples. So this is what we call a generative learning, and all of you who have been in touch with any unsupervised learning problem, you have done generative learning. And all of those models are generative models, right? So generative models are nothing coming from Mars. So they're as simple as the k-means clustering model. Okay? But the point is that if you use this model, and you generate new sample, that doesn't make sense, right? Because the model here is too simple, right? It is able to capture, for example, the clustering idea, but it's not really able to generate the complete data sample, right? So it's a very bad approximation of the data distribution. Everybody's clear? So, moral of the story, in unsupervised learning, you're essentially learning the complete data distribution, P of x. And when I say complete data distribution, if your data has no label, this simply means P of x, right? But what if your data has label? Then what would be the complete data distribution? It's the joint distribution, right? The distribution of your sample and its label, right? Everybody's clear? Questions? So when you are doing generative learning, you're essentially doing that. If you're considering a generative model, you're considering a model for these distributions, right? The complete distribution of your data, not only the conditional distribution of the label. So now that we have this kind of understanding, you can see that like supervised and unsupervised are not distinguished problems. Essentially, they're the same thing. The general framework is that you are always going to consider one distribution, one model for the distribution, and do maximum likelihood. But the question that might come to your mind is that, okay, if I have a supervised problem, probably I need to go for discriminative model. If I have an unsupervised learning problem, I need to always go for generative model. Well, you necessarily don't need to do that, because if you have the generative model, you have the stronger hand. When you have the generative model, you have the complete distribution. And you can always compute that conditional distribution that you want out of it. And even though none of you can remember of any generative approach for discriminative problem, it used to be there generative approaches for discriminative problems as well. And you can always get from a generative model into the discriminative model using the Bayes rule. So to give you a bit of understanding about that, let me just consider one setting where I have a supervised problem. So I have my data, and this data, there are samples, and corresponding to each sample is a label. Always think of image classification. So you have a bunch of images, each of them has a label, cat, dog, frog, and so on, right? So you have this data set, and instead of going for discriminative learning, meaning that you learn what is the probability of each class given the data, you just go for generative learning, okay? Meaning that you train this model. So I write it down PW, meaning that I assume some specific model describing the distribution of my data, and then I just use my data samples to train it by maximum likelihood. Okay? If I do that, I'm going to end up with some PW, and let's say that this PW is a good approximator of the true data distribution. Okay? Now, the question that I want to look into is that, can I get from this PW, this joint distribution that I have, can I get into a classifier? Can I get into a discriminative model that classify my data? And you might say, you might immediately see it by Bayes rule. So let's do it together. So let me just write down this first for you. I mean, everybody, we did it here, right? So everybody agrees on that, right? So the blue guy here, PW, is the model that I have trained to give me the joint distribution, right? Now, the red one that you see, this is the conditional distribution. This is the discriminative model that I need, right? It is going to tell me what is the probability of every class given the image that I have, right? And if I want to compute this based on the Bayes rule, I need to just replace the denominator. I just need to divide this joint distribution with the distribution of x, right? Now, that blue one, I do have it. That red one, I want it. What about the green one? Anyone has any idea how I can do it? Yes, you just marginalize the probability, right? So I can use the marginalization rule. So I can compute this probability of x by looking into this joint distribution and add it up for the x, for the given x. I add up every probability for all the labels, right? So when you do this marginalization, then you're going to have the probability distribution of x. So you don't need to develop any other model to compute that p of x, right? You essentially can compute it directly from your joint distribution, right? And then you can replace it here. Now this is going to be your discriminative model. So blue one here, I have it. Blue one in denominator, I have it. This is simply a summation or integral if y is a continuous variable. And I can always do it, right? This is not a big deal. I can compute this. And dividing this one by this one, I get the discriminative model. Meaning that if I give you a new image, x star, and you want to know whether it is image of a cat or dog, you simply just put into your generative model that particular image that you have, this x star is the image, and you want to know what is the chance of it being a cat, then you're going to put here as the label cat. And then in denominator, you're going to add up the probability of the same x, same image, for both classes of cat and dog, right? You add them up, and then you're going to end up with one probability, right? You again compute it for the dog, and then the one which is higher, you're going to say this is a label, right? So you don't need to go ahead and train a new model as long as you have the generative model, right? So this is why I told you you have the upper hand when you have the generative model. Because from generative model, you can easily get to the discriminative model. Everybody's clear? Questions? No question? Great. So, okay, we have time. So now that I told you the idea of getting from a generative model into a discriminative model, then let me complete it by talking about the Bayes rule. And I do know Bayes rule is very simple, but it is so important and so functional that it has, since its introduction in mid-18th century till now, it has just made impact on everything in statistics, right? So nowadays you say Bayesian point of view, Bayesian inference, everything like that. And all of it is just this simple equation, but this is really impacting a lot. Now, here in the left-hand side, this is the guy that I told you is the discriminative model, right? The distribution of the label given your data sample, right? And now the first and second fractions are the same thing we did in the previous slide, right? That is the definition. And the other one is just by replacing this p by the marginalized term. Now, the last one that we have here is again using chain rule, but this time you use it in the other way around. Okay? So p of x and y, if you want to open it, you can write it down as p of x times p of y given x. This is one way that we have it on the board. The other way is that I can start with P of y, right? P of y, and then I multiply it by P of x given y, right? I can do it again, right? So now, I have opened it up in the other form. So here, as you can see, I'm looking for P of y given x. I'm looking for the probability of the label given the data that I have. And I can represent it in terms of the probability of the data for every label, right? The very last fraction. Everybody sees what I'm doing here? Okay. Now, everybody on this equation, everybody has a name for it. And I'm going to explain it. These are the components of your generative model. So the first thing is the sample marginal that we have, that P of x. This is what we call it usually sample marginal, because this is the marginal distribution of x, your sample, your data sample, right? So how I can compute this sample marginal? I can just do marginalization, right? So this is the marginalization expression. So you usually do it by marginalizing the joint distribution, but I can always write it down in this form, right? So I can open up the joint distribution as the distribution of the label, the data given the label times distribution of the label, right? Now, one thing that is important here is the intuition that it gives you. The chance of one image happening is sum of the chance of that image happening, assuming that this is image of a cat, times the chance of cat being there, right? Plus the chance of this image happening, given we are looking for a dog, times the chance of dog happening, right? And so on till end, right? So you can write down the chance of your whole data in terms of class distributions, right? So cat image has its own distribution, dog image has its own distribution, and so on. Once you know them, if you collect all of them into a new data set, then you can compute the probability of this new data by just using this expression, right? So typically when you want to do data generation, we'll look for this one, right? So you would say, I want to generate one CFAR image, right? So you don't care what is the label. So it could be any guy inside CFAR. If you are looking for that, as long as you have this marginal distribution, you just sample from this one, right? Correct? Everybody's clear? Okay. So this guy, as I told you, is the sample marginal. The other one is this guy, which is our favorite one. This is what we call it label or class generative model, which means that I fix the label. I would say I am looking for a cat, right? And then I am looking at the distribution of the image, assuming that the label is cat. Everybody's clear? So this is what generates your data sample given the label, given the class. And this is why we call it class or label generative model. Clear? So how I can compute it, I can always compute it directly from the joint distribution. So this is why both of this guy and this guy, both of them are called generative models. One of them is for, for any label, and the other one is for a given label, right? It's the only difference here. You can always compute it with this by this expression. This is the one which we are looking for when we want to just generate one specific class image from or data from one specific class, right? So I tell you I want an image of a cat, right? And then you want to be able to just fix your label to be cat, and then you sample one image of a cat, right? You just generate one cat image, right? Everybody's clear? So this is what we call it the label generative model. One thing about this is that sometimes that guy is easier to be modeled as compared to the discriminative model. Like it's easier for us to think, okay, if we know that the label is a cat, then which pixels are going to be on, which pixels are going to be off, right? So you remember the digit example we had last time, right? And if I tell you that, well, the label is 1, then you do know what is the chance of every single pixel, right? Only one going to be there, right? So you know that the configuration of on and off pixels, which gives you 1, is going to happen. Anything else is not going to happen, right? So if I fix the label for you, I tell you this is 1, then you know what is the distribution, right? So sometimes it's easier for you to describe the distribution to put some assumption on this distribution, on this model. Question? Yes?
The example of 1 that you've given is pretty straightforward because 1 is, particular number and
Yeah.
there's no way about it, any other way about it. But when you're talking about a cat, there is a degree of randomness in it, isn't there?
Definitely. I mean, you don't think directly about the pixels, but if you, we're going to see like when we go deep in the course, but if you are dealing with the latent space, then latent space has this property, right? If it's a cat image, it's going to get them concentrated at some part of the latent space, right? And then you're going to say, okay, if it is a cat, then I'm going to be there, and then maybe I can think of a Gaussian variable there, and then I just sample from there, right? And then I decode it, and I'm going to get a cat, right? Yes?
How do we learn this model? Like, is this like the model that we learn in, like, for example, class condition latent diffusion model?
Somehow, but there is a bit of trick there happening. Yeah, we are.
You cannot marginalize X, like, right?
Yes. This is why we do variational invariance. Yeah, so we're going to talk about it. Like, it's not as easy as I'm saying here, but there is always a trick to handle it. The point is that in this case, you don't have the huge computational issue. So you don't, computation or say complexity of the data is not an issue anymore. Lack of information, lack of knowledge is the issue, and you can always assume something. But in the other way around, you always has the, like, computational is invisible. I'm going to give you the simplest example possible in the next section, and then you're going to see why this is happening. Okay? Questions on that? So keep this last one in mind. So sometimes it's easier to model the generative model, and then this is going to help us in the next section when we are talking about naive Bayes. Now, the next thing in this equation is this py, and this py is what we call it label prior, right? A label prior is a prior belief or kind of approximation you have on your label, right? So for instance, in MNIST, you would say, okay, I assume every digit is happening with the same probability, right? So how do you assume that? Why you assume that? Well, you are always either very faithful, so you would say, okay, everything is going to happen uniformly in this universe, or you just get the data set, and then you see how many zeros you have there, how many ones you have there, how many twos you have there, right? And then you divide it by the total number of samples you have. All of them have the same frequency, right? So always you can find it either by putting some assumption or by doing some empirical calculation, right? Just experimental calculation. And unlike the other case, unlike P of X, this one is typically not an issue, right? So for image classification, X is the image, right? And the space of possible images is incredible, right? It's huge. You can never think about the numbers, right? But when you are thinking about the possible labels, that is always something that you can handle, right? C400 has 100 labels, right? ImageNet has 1,000 label, right? So it doesn't matter how complicated your data set is. At the end of the day, you have a finite number of labels, and you can empirically check, like see how many of them are cat, how many of them are dog, how many of them are frog, and so on. And then you get an empirical distribution, and then you take it as the prior beliefs. You would say, okay, I assume that every label is just happening with that frequency. Okay? Everybody's clear? So, important thing here is, thing here is that this prior belief is not a very complicated thing to compute in practice. unlike the P of x, which is complicated, because if you want to approximate based on your data set P of x, lots of those x's that are valid points inside your data space are not happening at all, right? So you have no information about them whatsoever. Questions? Great. So the last thing is the discriminative model, which in the Bayes formulation, we usually call it the posterior distribution. So it means that you want to know posterior, after you see your data x, you want to know what is the label, right? And this is the one which you can always compute it using the Bayes rule, right? So this is the discriminative model when you are, you need it if you want to infer the label of your data. So if you want to know what is the label of this image, you really need to compute this posterior. And when you do discriminative learning, you just directly assume that you have a model for this guy, right? So you assume that you have one classifier which is describing this distribution, and then you look at your data set and you try to just train the model based on that data set, right? The key point here is that when you have the generative model, if you have the generative model, as I told you before, you have the upper hand. You can simply use the Bayes rule to compute this posterior. That is easy for you. But the other way around is not always correct, right? Just think about having P of y given x, this posterior, and you want to compute P of x and y. What do you need to know? P of x. And it's impossible that you can make it, right? If you don't have P of x and y, you cannot find P of x, right? Because x is huge. The space of samples is huge. So you can never approximate it from your data easily, right? Unless you train another model, right? So you cannot empirically compute it. So the other way around is usually not the case. And this is the whole beauty of the Bayes rule, right? So you're going to get from, you're getting from impossible to something possible, right? And this is the reason that despite the whole simplicity here, it has impacted the whole statistics so much. Questions on that? So everybody's clear about all components of the generative learning? Great. So if you got no question, then one last thing. So as I told you, it's not always the case that when you have a supervised learning problem or discriminative learning problem, you're always going to train a discriminative model. So you can use a generative model to do a discriminative task. And then you might ask me, is there any particular example? Yes, the most famous example is the naive Bayes. Naive Bayes is the most stupid generative model you can think for your data, because essentially you don't learn anything, right? You just do everything based on your data, data set. There is no parameter involved there. And the thing that I want to do now is to just go over the naive Bayes, because I have this feeling that whenever I just explain naive Bayes and compare it to discriminative learning problem, then everybody gets clear about the order of complexity that the two generative models and discriminative models are going to represent. So we're going to do next naive Bayes. So this is the, say, the most stupid generative model you can think of. And once you understand it, then we are ready to just land for deep generative models.